Hello, everyone. Today, we will discuss Section 4 of Chapter 4, PoW consensus algorithms. PoW consensus algorithms are mainly based on proof of work, PoW. The concept of proof of work was first proposed in 1993. Initially, the purpose of PoW wasn't to implement cryptocurrency, but to prevent spam. In 2009, Bitcoin adopted proof of work as its consensus algorithm to validate transactions and broadcast them to the blockchain. As a result, Bitcoin became the origin of blockchain thinking. Now, PoW has expanded to many cryptocurrencies and has become a widely used consensus algorithm. In Bitcoin, the consensus mechanism of PoW is not aimed at final confirmation, but is based on probability, which means eventual consistency. To understand Bitcoin's consensus process, we first need to clarify the concept of mining. Mining, as you all know, is when miners compete to generate new Bitcoins by solving computational problems. To ensure that a new block is generated approximately every 10 minutes, the system must adjust its mining difficulty as computational power increases. Mining consists of three main parts: generating the Merkle root hash, assembling the block header, and calculating the proof of work output by finding the random number, knots. Based on the above mining process, Bitcoin's PoW consensus mechanism completes bookkeeping in the following way. First, clients generate new transactions and broadcast them to all nodes in the network. Then, the nodes in the Bitcoin system receive the transaction message and write the transaction into the block. Next, the nodes mine by finding a suitable knots. When a node finds a valid knots, it broadcasts the proof to all network nodes. Other nodes verify the block, and if accepted, they start a new round of mining based on this block. As we all know, Bitcoin was invented by Satoshi Nakamoto. When Nakamoto designed Bitcoin to incentivize people to keep the ledger, he introduced transaction fees and block rewards. Therefore, whoever can package their own ledger and link it to the blockchain will earn these rewards. To compete for the right to package blocks, every user must perform proof of work, i.e., solve a mathematical problem. The first person to solve it wins the reward. Now let's analyze what this mathematical problem actually is. In fact, it's a technical term called hash function. We've discussed birthday collisions before. For example, if there are 23 people in a class, there is more than a 50% chance that two people will share the same birthday. Moreover, regardless of a person's name, nationality, or ethnicity, their birthday is always formatted as year, month, day, and the length of the birthday is fixed. In computer science, there is an operation similar to finding someone's birthday, and it's called a hash function. It can convert any string into a fixed-length number. For example, if the input is false, it will be converted into an 8-character string after hashing. If the input is "the force runs across the ice," the hash function will also convert it into an 8-character string. If the sentence is changed to "the red frost was across the ice," after hashing, the output will still be an 8-character string. Thus, hash functions have two characteristics. 1. Regardless of the length of the input string, the output string's length is fixed. This is a key characteristic. 2. The forward calculation of the hash function is easy, but the reverse calculation is extremely difficult. For example, if we take a decimal number, cube each digit, sum them, divide by 256, take the remainder, and then convert it to binary, that's an 8-bit hash function. But given any specific time value, calculating this hash value is not difficult. We can calculate it manually ourselves. However, if I give you a hash value and ask for the original number, it's very difficult to reverse engineer the value. Because of these features, hash functions are widely used in computer science, such as in digital signatures and other fields. Now that we understand hashing, we can use it to explain the mining process in detail. Firstly, every block on the blockchain has two parts: the header and the information. Miners involved in mining will read the header of the previous block, then add their collected transactions, packing time, personal information, random parameters, and so on to generate a string. Then, users perform a double SHA 256 hash operation on the string to obtain its hash value. In Satoshi Nakamoto's white paper, the design requires that only those who calculate a hash value smaller than a specified value, the threshold, are considered to have met the conditions. If you find the hash value, congratulations. You now have the right to package your block and link it to the blockchain. At this point, you provide the string and the corresponding hash value and broadcast it to everyone. After verification, the block is linked to the blockchain, and the hash value you just calculated becomes the latest block header. In the next round of mining, all miners in the world will read the data block header and add it to their own string, then proceed with the next round of hashing. Of course, in this calculation, how can one get a hash value smaller than the current value? As we analyzed earlier, hash values cannot be reverse engineered. Thus, the only approach is brute force, changing the random number continuously and testing to see if the result is smaller than the threshold. It should be noted that each miner faces a different difficulty when mining. Although all miners read the header of the last block on the blockchain, their transaction information, timestamps, and personal information are different. This also introduces an element of luck. Some miners may be lucky and find the correct value after only a few tries, while others may have to try thousands, tens of thousands, or even hundreds of thousands of times. This involves the issue of difficulty adjustment. When Satoshi Nakamoto designed Bitcoin, he wanted to ensure that Bitcoin would not be overproduced, as Bitcoin is unique and scarce. If too many Bitcoins were produced, their value would decrease. Therefore, it was stipulated that a new block would be produced every 10 minutes. However, we have to understand that the computing power of computers is constantly rising with the changes of the times. How do we keep this time constant? This is where difficulty adjustment comes into play. As we mentioned earlier, the SHA 256 algorithm can convert any string into a binary number, where each bit is either 0 or 1, making each possibility have a 50% chance. If we require the hash value to have the first n bits as 0, the probability is 1 over 2 to the power of n. In other words, on average, we would need to compute 2 to the power of n times to get a hash value with the first n bits as 0. We can adjust the difficulty based on the global mining power to ensure that the packaging speed doesn't become too fast or too slow. If there are too few miners, the value of n will be reduced, making computation easier. If there are too many miners, how to do it? If there are too many miners, the difficulty will increase by raising n. For example, if there are 10,000 mining machines in the world, each with a computational speed of 14 terahashes per second, 14T/s, then all mining machines together can perform 8.4 times 10 to the power of 19 hash calculations in 10 minutes. To ensure that it takes about 10 minutes for 10,000 machines to find a result, the difficulty will need to be set to around 66 bits, meaning the first 66 bits of the hash value must be 0. Alright, everyone, that concludes the content for Section 4 of Chapter 4.